So much pressure. Well, you see, this is funny because Brea is going to try to be quiet and not have me say anything, and Chloe is going to crank up the show so she can be the star. I saw a video last week that tells me a whole lot about that. Okay. So as I just said, the purpose of this experiment, the purpose of this particular unit is to is for you as chemists to be able to look at a chemical formula, do a Lewis diagram, think about what it looks like three-dimensionally, use our knowledge of electronegativities to tell whether it's polar or not, and once you've determined that, we then should be able to think about the physical properties, the macroscopic properties that we can observe about these particular substances and be able to make predictions on it. Because that's what makes a good theory. If the theory does not successfully explain what we see in nature, then it's not a good theory, all right? So I'm teaching you how to take the theory and then in the end explain what we see in nature. Okay. So just like last year when I taught this, I would have talked about the difference between inter and intramolecular forces. So intra, the prefix again means within or inside. So today's lesson is not about intra, it's about intermolecular forces, which is between. But this little note is to just contrast them, and I would have talked about this last year as well. So up to this point in this unit, we have talked about intra, ionic bonding, right? That was the very beginning when we were done talking about the atoms and electron configuration and all that. We talked about how, a sodium gives its electron, its s electron to the chlorine. It puts it in its p orbital, which fills the outer shell. They become oppositely charged things and they stick together. Ionic bonding. And then covalent bonds, and that's what we've done all the way up to this point. Sigma bonds, pi bonds, hybridization, covalent bonds. So we've learned great detail about intramolecular forces that happen within or inside a molecule. All right. And what we want to talk about today is intermolecular forces. And this is what happens between neighboring molecules. Now, I'm introducing you to another term, name of a scientist who first kind of mathematically explained intermolecular forces. So these are sometimes called van der Waals forces. Again, I think it's a Dutch name. They pronounce it van der Waals forces, van der Waals forces. It doesn't matter. So again, inter means between. They're the attractive forces between neighboring molecules. These are broken during physical changes. They depend on the type of molecule. So this is the type of thing that allows water to be liquid at room temperature, and then our methane gas, say, coming out of the tap of our Bunsen burner, why it's a gas, or even the lab bench, why it's a solid, all right? Intermolecular forces are much weaker than intra, right? So the chemical bond that holds the hydrogen onto the oxygen in water is a lot stronger than the hydrogen bonding that holds the water together. This makes good sense. As we heat water up, the first thing it does is it boils, so the water molecules separate from themselves, and then if you were to continually heat that water vapor to very, very, very high temperatures, eventually you'd cause a decomposition and the hydrogen would be pulled right off of the oxygen. But in that progression of starting at low temperatures to high temperatures, boiling takes place first, because inter is weaker, and then you go to very high energies, and then you start causing chemical changes. Okay. This is just a classic image that represents the difference between an inter and an intra. I will add some lone pairs to this just so that we can get a feel for what I'm drawing here. And then also, just to finish it off, there's a slightly negative end on the chlorine due to the chlorine's higher electronegativity, a slightly positive end, and a slightly negative end. And it is those dipoles, in this case, that results in the intermolecular force. Now, if you're writing ahead on your device, I'm going to shorten up the next slide. It's very redundant. So you might want to just pause until I tell you what to write. Because again, sometimes we write the same thing over and over again, and it does not need to be written. Okay, we got our diagrams. So don't write yet. Let's talk about what we want you to write. So physical state and relative melting and boiling points depends on these attractive intermolecular forces. So the higher the intermolecular forces, the higher the melting point and the boiling point. And that's what we're going to be comparing in our lessons today. We're going to ask which has the higher boiling point or which has the higher melting point. It doesn't really matter. It's going to be an indication of which one has the strongest intermolecular forces. So I think we don't need the first bullet. I think we could probably just get away with writing writing what's in the boxes. And I don't think the bottom bullet is that useful either. It's true when we change state, that's what the energy is required for. But in this lesson, I'm more interested in what has a higher boiling point, what has a higher melting point. Can you use your knowledge of shape and polarity to make appropriate predictions? What's that? A melting point and boiling point. So I don't have it defined there, but you can write it if you want. MP stands for melting point, and BP stands for boiling point. That temperature at which it melts or boils. So again, if something is a solid, it means it has very strong attractive forces between them. Again, here I've got the desktop, and I can't push my hand through the desktop. I can't walk through the desk because obviously whatever particles are making up that desktop, there's very strong attractive forces between them that I cannot push through. All right? But if I jump into a swimming pool and I try to run around and chase somebody around, I can work my way through the water, but it takes a little effort in that I have to work against the attractive forces of those liquid water molecules that they're being held together by, and therefore it takes me a bit to get through, and their melting point and boiling point would then be moderate somewhere in the middle. And then gases with very low melting points, well, they have to be low because at room temperature we must have transitioned between that liquid becoming a gas, so that at the temperature we're at, it's a gas. Low melting point, weak attractive forces. It takes no effort for me to walk through the air, walking back and forth in front of you in the class, and that's because those particles are not held together very strongly. They will easily get out of the way for me, and I can then walk through them. All right? Again, my ability to walk through something does have a direct relationship with melting point and boiling point. It's those same attractive forces that I am overcoming as I push through them. Okay? So let's talk then about the different types of forces. And the first thing we're going to talk about is London forces. Now on the next slide, there's a bit of a picture, and we're going to look at it, and then I'll come back to this slide and I'll draw it on there again, just because I'm making the video, and I'll just show you how you can draw that up and how to explain it. Now it says, due to the attraction of short-lived induced dipoles created by the random motions of the electrons. This is different than what I would have said last year. Last year I just said, the electrons from one atom are attracted to the protons of the other atom. And I left it at that because I didn't want to get into detail about what are called induced dipoles. All right? So let's take a look at the picture on the other page, and then I'll come back and I'll draw it so that you can see kind of how I'm drawing this. And then we'll come back, we'll write this down later. So I took this out of a textbook, and so we have an orbital that then contains electrons. In this case, it's got 3 electrons in it. I don't like the looks of that. I'm going to draw it with only 2. And normally they're buzzing around, say in an s orbital, and they're just buzzing around there doing their thing. We really don't know where they are, and we really don't care. But due to this probability idea, there will be a point in time where both of the electrons at some point in time will be on one side of the nucleus and not on the other side of the nucleus. That's just due to the randomness of the way in which the electrons move. Now, if it happens, here it is happening on the right, we produce what is called an induced dipole. It's just happened to create a dipole. And due to the delta positive on one end, it's going to change the probability for the other atom, and it's going to cause its electrons to also move to the same side that it's attracted to, and thus create also an induced dipole. So one kind of accidentally gets created, but the atom that's nearby it will then all of a sudden shift in such a way that another dipole is also formed. This is very short-lived because the electrons are going to randomly move away, but it is enough to create a tiny little bit of attraction. So how should we draw this? All right. So I'm going to bring this back up to here, and I'm going to just draw a circle with my plus there, and I'm going to just draw 2 electrons, 1 on each side. Okay, that's my nucleus, and those are the electrons. And beside it, I am going to put this oddly shaped orbital with my plus here and my 2 dots on that side. And I got to be careful the way I write here so I don't mess it up. Okay? This is going to create a tiny slightly negative and slightly positive. In my next picture below it, I'm going to draw, oops, not that color. I'm going to draw the same thing on the right. We'll put a little arrow down, plus, dot, dot. And now on the left, I am going to draw the same thing, plus, dot, dot. Slightly positive, slightly negative, slightly negative, slightly positive. And I will put a tiny little dashed line in between. There is the weak attraction right there. And I could label the heck out of it, but it's all above it. These are short-lived induced dipoles. And moments later, they'll be gone. But they are enough to explain a very weak attraction. Okay? We have that diagram. Now, I used to teach this based on an old textbook, and it used to get very, very excited about counting electrons. But I recall in university, and this textbook also goes down that path, the more electrons, the greater this effect is, because it means they can slosh around even more. So if I've got an atom with lots of electrons in them in all kinds of different orbitals, that sloshing of the electrons, kind of like sloshing of water in a cup as you're trying to, let's say you're trying to walk with a cup of water on a moving boat, right? That's going to all slosh around. The more electrons there are to slosh around, the stronger this effect is, okay? But the more electrons means it's a heavier thing. Because if we think about when we count electrons, as we move down the periodic table, there's more and more electrons in those orbitals, and it gets heavier and heavier because there's more protons and neutrons. So a very simple way to describe the effect of London forces is to simply look at their molar masses. Looking at their masses is a direct measure of the number of electrons. And I recall in university them not even mentioning electrons, but mentioning more about their masses. So I now have students analyze it in terms of the masses. The heavier they are, the more electrons there are, and the greater this effect is. You can write that down. Again, I'm seeing lots of phones and I'm seeing lots of texting. You guys are seniors. Again, we're rolling into important parts of the year here, and I'm going to let you be adults. So like I said in the past, and that's why I'm making a new video, the video that's on there right now has me with slides and slides and slides of examples where we counted all these electrons up. And it's much easier because we're better at it. Just look for the molar mass. So essentially, I'm telling you that if I'm asking you to compare the London forces between molecules or atoms, determine the molar mass. And the heavier it is, the stronger the London forces will be. And if it's only London forces acting on it, and we don't have any dipole-dipole or anything like that, then it should have the higher melting point, boiling point. It's simply that logical and that easy. A very common and easy example to look at is comparing F2, Cl2, Br2, and I2, and ranking them in order of increasing boiling point. So I'm just going to make a quick little chart, right? Oop, I don't want it to be red chart. F2, molar mass. Which means you need a periodic table in order to play the game. Unless you can see it here. Pretty big, 19 for 1F. They're both 2s. I guess we could just look at 1F, but let's calculate it. Let's multiply it by 2. What is that, 20, 38? 38? Did I do that math right? 19 times 2, 38. $38. 38 grams per mole. Cl2, Br2, I2. You got numbers? 71. 71 grams per mole. You have a next one? What is it? 79, 80 times 2, 160? Yeah? Yeah, 80 times 2, 160. And iodine, what is that? 127 times 2, 240, 254. 254 grams per mole. So according to what I've told you, iodine should have the highest boiling point. Fluorine should have the lowest. So if I'm ranking increasing, low should be F2. Working my way up, Cl2, Br2, and then ultimately I2 with the higher boiling point. Boiling point. Okay. It's that simple. Check the molar mass and see how it ranks. If we look at our periodic table, you can see that trend. Gas, gas, liquid, solid. And that is the exact effect of that increased number of electrons, same as the increased mass. I can actually find the boiling point, I think, on this guy. Covalent radius. Boiling point is the second last line. Negative 188, negative 35, 55.8, 184, and we stop there, 184, 337 for astatine. Okay? It takes not much to find a textbook or Google to find a relationship between them, and you can see it's almost linear. I know this doesn't have like it doesn't necessarily have an x-axis of the molar mass, but it's pretty close to being exactly linear. There is a demonstration of the effect of how the increased mass increases the electrons, increases the London forces. Okay? All right. Okay, so let's take a look at some hydrocarbons. Now, finding the molar mass seems almost silly here because you can see there's more carbons and more hydrogens. Which one's going to be the heaviest? Yeah? C3H8. The lightest is going to be CH4. Maybe just for the sake of doing the doing the calculations, let's do it, but it shouldn't take us too long. There's that one there. But obviously, they're getting heavier with the more atoms there are. So therefore, C3H8 should be the highest. Six plus 12 times 2, C3H8, 8, and then 12 times 3. And again, I don't want to waste your time. Some of you don't have calculators out, but you know how to calculate a molar mass. This is going to be what? 16 grams per mole. This is 2430. Right? And what's that one? 36, 44? 44? 44 grams per mole. Therefore, what's the highest boiling point? C3H8. All right? So again, if we go from low to high, CH4, C2H6, C3H8, up to a high boiling point. All right? Again, it's pretty straightforward. Again, this information is very well known. you typically, if in university, you typically come across this in an organic chemistry unit. We're doing organic chemistry next. Again, to just express how hydrocarbons change in terms of their intermolecular forces as they get larger and larger. If we were to look at the actual data, you can see it there. Again, I just Googled it. And this is a graph of temperature versus the number of carbons, because the more carbons there are, right, the heavier it's going to be. And we did the first three here, 1, 2, 3. And you can see here it's not perfectly linear. There is something about that once it gets so heavy, it doesn't increase anymore. These are melting points, all right? These are melting points here. And you can see that there's some fluctuations there in the melting points. I might have been taught why that is at some point in time, but I can't remember. I'm not that concerned. The heavier it is, the higher the melting point or boiling point. Okay? All right? Pretty straightforward stuff. So that's for London forces. They are the weakest, but they can be quite strong. You can see, if I just go back just for a moment, you can see if we've got something that has 40 and 50 carbons, right, we've got a melting point that's like 500 to 600 degrees Celsius. Like that, that's a boiling point. That is high. That is hot. So these big molecules, even though they're nonpolar, can have still very high melting points and boiling points if they're really big. Okay. Dipole, dipole. So I'm working my way up in strength. Dipole forces are a little stronger, well, a lot stronger than London forces. Dipole forces exist between oppositely charged dipoles in neighboring polar molecules. The strength of the dipole force depends on the polarity of the molecule. In this course, we are going to use the size of the delta En in order to determine that polarity. That is a simplistic view of the way that molecule behaves because it does have three-dimensional structure, and we should add those dipoles up, but that can be done with a different professor at a different level. We're just going to quickly calculate delta En in order to compare that for test purposes. And for simple linear molecules, especially diatomic, that does work quite nicely. Again, this is just a little graphic representing how these dipoles can be attracted to each other. These are simulating HCl's. I don't think there's anything that necessarily needs to be drawn there. In that example that we did at the beginning where we were drawing the difference between inter and intra, that was a dipole-dipole force between those HCl's. Dipole-dipole forces are only 1% as strong as a covalent bond. So again, they're much weaker than covalent bonds. Okay, let's do a couple of examples of these. Now this is an iodine and a chlorine. It's just the way the font that I choose looks to be very similar. The I and the CL and the L, the lowercase l. If at any point on a test you're not sure whether something is a carbon or a chlorine or something like that, let me know. I could clarify. In this case, we are going to take a look at, let's look at molar mass still, but then let's also compare it to a delta En. So we're going to look for two things in this case, because remember, London forces exist between all things. So everything that we deal with has a molar mass. That's going to affect London forces as well. So then Br2, and then I bonded to a Cl. And now some of you are moving to get your tables, which is good. If you need a table, I got some extras sitting up here. We had Br2, didn't we? That was like 80. 80 times 2, that's 160. Yeah, me. Should sound interesting. I and a Cl, 127 plus, what is that, a 36? I can't do that in my head. Somebody got a number there. 162, whoops, 162. So I would say their London forces are pretty close, all right? And delta En, 0. And what is it for I and Cl? What do you got? Don't have anything? No? I'm subtracting the ENs, right? What do you got? 0.5? 0.5. All right. So that makes this particular bond here, right, means it's polar. And therefore, I would say that the ICl, which is even heavier, it's not much though, should have a greater boiling point than the Br2, because this is definitely polar. Okay, so if I'm ranking in increasing boiling point, low would be Br2, and then ICl, high boiling point, BP, and it's due to the fact that ICl is polar and therefore dipole-dipole forces. ICl is polar and will have dipole-dipole forces. Dipole-dipole forces. Okay? All right? Pretty straightforward. Nobody saying anything? All right, let's do one more of these, and then we'll talk about hydrogen bonding. So again, do the same with this. Find a molar mass. Find a delta En. chlorine 35.5, so that is 36.5 grams per mole. HBr 80 plus 1, 81 grams per mole. Delta En. What do we got for delta En of HCl? Somebody have a number there? 0.96? 0.96. That was the one we did when we were talking about polar bonds. What's the other one? 0.76? 0.76. All right, what do you think? Yep. Based on the delta En, but then there's an effect here as well, right? So for something like this, I would expect, difficult to say, unable to decide. One has greater London forces, which would increase its boiling point. The other one has greater dipole-dipole forces. Difficult to say. I really don't know what it is. Could somebody do a Google search on the boiling point? What is the actual boiling point, BP, for HCl? So just Google boiling point for HCl or hydrogen chloride, and then boiling point for hydrogen bromide. So HBr has stronger London forces, and HCl has stronger dipole-dipole forces. Does anybody come up with some numbers for the actual? What do you got? We're in Kelvin, 189 Kelvin. I'm okay with that. So that's again below zero, right, which was 273. And what about HBr? 206 Kelvin. 206 Kelvin. So you can see they're close. They're 10 degrees from each other. And therefore, our hypothesis, I don't even know what I wouldn't hypothesize anything. So there's the actual values. So in this case, London force is greater than the dipole-dipole interaction, but you can't really just subtract. I'm giving you guys kind of a very simplistic view of how to analyze it. So in this case, I'd expect you to say, I can't predict what the ranking of the boiling point will be because one has stronger London forces and the other one has stronger dipole-dipole forces. And you do not have enough knowledge at this point to be able to distinguish the ranking. All right? Any questions or concerns? Okay, so that is the effect of dipole-dipole. And this is a little different than last year. Last year I would have said dipole-dipole always stronger, right? But now I'm saying London forces can be strong depending on that size. So we got to be a little more critical. All right, hydrogen bonding, again, which is a type of dipole-dipole. It is a strong, very important version. You can write all of that down. I don't know whether that picture is worth copying. Again, it's just showing that when we have nitrogen bonded to hydrogen or oxygen bonded to hydrogen or fluorine bonded to hydrogen, that intermolecular force becomes very strong. Again, the common error for rookie students is to think that the bond between the nitrogen and the hydrogen is the hydrogen bond, but it's not. It's the bond between the hydrogen of one molecule to the nitrogen or the oxygen or the fluorine of the other molecule. So it's them sticking together. So that thing in there is what we call the H bond. And it's about 10% as strong as a covalent bond, which makes it 10 times stronger than a regular dipole-dipole interaction. It is significantly stronger. So one example, and then I'm going to show you a graph again of some information, and then one more slide, and then I'm done. There is a last slide. I'm not going to get you to write. I'm just going to talk about it a little bit. Okay, so let's do one example. Oh, wait a minute. Nope, that slide, then what? Sorry, there's an extra slide in there. I forgot. You got to write that down. I jumped the gun. This is an important one. H bonding is much stronger. So I'm telling you essentially that if you've got an example of something H bonding, it's going to have the higher melting point or boiling point. Now I'm going to support that with some data. And even though I'm just giving you a blanket instruction, if you get one of those that is H bonding, then it'll be much higher than its related chemical. But it's true. I don't know if you've noticed, but I've been always getting you to compare things that have something related about them. It's difficult, and I'm definitely not going to get you to compare, say, the boiling point of bromine with, say, the boiling point of C3H8. You see what I mean? They have nothing in common. So there's no way to really compare them. I've always had you compare things that have something in common. All of the halogens, or all of the hydrocarbons starting with one carbon and then two carbons and then three carbons. I had you compare a bromine with something that contained an iodine and a chlorine, right? So again, we've got all the halogens there. There's a term for when we compare things that have something in common. We call it a homologous series, all right? The prefix homo, something is truly the same about them, that they're all halogens or they're all hydrocarbons with increasing numbers of carbons, all right? So I'm not going to get you to compare things that are totally, oh yeah.
We're going to continue our emergency response drill. So at this point, we are going to do a hold and secure. So with all teachers up to this time, remember this is just a drill. With all teachers doing so, a hold and secure at this time. We'll come back on the video. Thank you.
I think I'm locking doors, but we can continue. There's nothing special about a hold and secure. Just going to make sure this door is closed. But I'm pretty sure. Let's make sure it's locked too. I think so. I really don't remember. Haven't done one of these in a long time. Okay. So, let's do an example. Again, I'm not sure where we are in the writing process, but we're close. Oh, don't worry about that. Don't worry about that. Those are just biological things that have hydrogen bonding important. In biology, it's not that important. It's just squishy stuff. Keeps us alive, you know, stuff like that. So again, I'm kind of giving you a breakdown on how to do this stuff. Again, molar mass, delta En. Now, in this case, I'm going to tell you that the hydrogen bonding in water is going to trump everything, and therefore it's going to have the highest melting point and boiling point, because that's what I just told you to do, and that's what your answer is going to be. But still, I want to just do a comparison here. So notice this particular little homologous series. Again, what we have in common here is that we've got a group 16 element bonded with hydrogen. So it's the same kind of molecule, except we just are using a heavier and heavier atom. 18, that's an easy one. And sulfur is 32.1 plus 2, 34.1 grams per mole. You don't know how to do a delta En?
Oh, I did it in my head.
You don't, yeah, use your calculator. Is that for the second one? 0.38? 0.38. And what's the first one? 1.24? 1.24. Okay. So there's that very high delta En for the water, which indicates that it's hydrogen bonding. You can see here this falls under the non-polar now that we use the textbook that we're using. Even if we were using the last textbook, that was 0.2. It's just weakly polar. It's got greater London forces, but we're going to just say H2O has the higher boiling point due to H bonding. All right. In other words, if I give you a question like this, it's a bit of a trick question in that you should see that that's hydrogen bonding and it's going to have the highest melting point or boiling point. Now that may sound like I'm just giving you a blanket rule and not having you think about it, but let's take a look at the actual data. If we take a look at the actual data, here we've got, again, the homologous series. I'm looking at the one in the middle here. This is O and then S and then selenium and then tellurium. So again, boiling point, degrees Celsius. No, that's terrible. Look at this. 373. It's not degrees Celsius. That's a Kelvin temperature. I assume the rest of them are Kelvin temperature, because 373 would be 100 degrees Celsius. So it's got to be Kelvin. So that's got to be error, but it doesn't matter. 373, and then it drops way down, 213. So there you can see it. There's Kelvin, there's water, and then boom, way down. And then even if we go all the way down to tellurium, it never gets back up to the hydrogen bonding effect. So the hydrogen bonding effect is great. That's experimental evidence supporting that. Same thing with the ammonia. NH3 drops way down, and as we move up its homologous series, and that we're putting phosphorus and arsenic and antimony, again, it doesn't quite get up to that particular temperature. We see the same thing. It's not on there, HF, 19.4. That's got to be That might be degrees Celsius. This is funny. It's all kind of messed up. But there you can see, and then it drops way down and still doesn't get back up to that effect of hydrogen bonding. And when we graph anything else like that, if we graph carbon with hydrogen, we don't see that effect. All right? We don't see the carbon with hydrogen being much higher than the other ones. Okay. Don't worry about writing this down. I've changed my mind. So water is special, though. Water can, due to its shape, form 4 hydrogen bonds with adjacent water molecules, where NH3 has that trigonal pyramidal, and there's not enough room to get so many molecules around it. So water is really, really special in that it can really form lots of hydrogen bonds, and that makes it, even compared to NH3 and HF, also much higher boiling point and melting point, which allows water to be liquid at room temperature or at regular temperatures. So it can exist as a liquid on the surface of the Earth, and then sometime in the past, some molecules, something in a goop of something came together, formed some life, something important about life and biology and water and all that good stuff. As a chemist, we don't care about that. But liquid water on the surface of the Earth is very important to us being here. Okay. Just the last little bit of something here. There are other properties that are affected by this hydrogen bonding or any intermolecular forces. Surface tension, that's the ability of the liquid to kind of hang on to itself. It allows it to kind of stick together. So I've shown you this before. If I take some water and I put it on the desktop, right, it literally piles up on the desktop. And so from your vantage point, if you get down to the level of where the water is, you can literally see a pile of water on there, and that's because of the surface tension. Where something like gasoline, which has low intermolecular forces, would spread out and do its thing. Capillary action has something to do with liquid being drawn up in a tube. Again, that's very important to things like trees and that want to have water brought up from the roots in order for it to live or something. So again, water can do it very well. Viscosity, that's that ability to flow or resistance to flow. And again, related to its intermolecular forces. Vapor pressure has to do with how easily it can evaporate, all right? So things that have low intermolecular forces evaporate very easily. They have a very high vapor pressure. Things that have high intermolecular forces, they don't evaporate very easily. I'm not going to ask you questions on this. You may see questions in the textbook about these things. Really, it's another way of asking you about the intermolecular forces, okay? The higher they are, the stronger these things are. All right, and there is a worksheet, I believe, that we started on the last lesson, and then there's some textbook questions. And I am done.